My subscribers, awaken, for I am back. Back from the prison I call college. I just got done with my finals for this semester, so I am back for Christmas break or winter break. So, yay! I get to record again. I wasn't able to find a place to record at my college. So today we are getting into machine learning within Roblox Studio. Machine learning is a very complicated concept as a whole. We're going to be touching the very basics, the simplest neural network neural network that you can make that learns very simple patterns. Just because I say it's the simplest does not mean it is simple. It just means that this is where people normally start on their journey to learn about machine learning. And I'm going to take my shot at teaching you guys that very basics. And the very basics being how to create what's called a perceptron, which is probably the smallest neural network you'll ever make. So let me show you a graph of what the perceptron looks like visually. Okay, so this is the visual graph of our perceptron. So these circles here are what we would call a neuron. Don't worry about the name logistics of it. Neuron sounds like it's something really special. In this example, what I'm going to show you in Roblox Studio, it's just a number, and it just takes the input we're going to give the neural network when we're wanting it to make a decision. So just think of the neuron as a number. In this case, it's our input 1. In this one, it's our input 2. This neuron down here is a little bit special. So it's connected differently than the others. Instead of taking an input, the number this bias will be is always going to be 1. In the code, we're just going to ignore this entirely, but this is just the visual representation of, we call this the bias neuron. And then you see that these neurons are connected to the output neuron, which is going to be the one that gives us the answer when we give it input, what the neuron or the neural network decides it chooses for the answer that it spits back out at us. And all the neurons from the different layers, this is called input layer, this is called the output layer. The input layer is all connected to the output layer, and we connect it visually through weights. This is the first weight, second weight, and the bias weight. We will just call this the bias. It's not necessarily the same as the weight, but anyways. So it looks like it's visually connected, but really the weights are also just numbers, including the bias. When you do the calculations for getting the output, you just multiply the weight by the input. So the ones that are connected at least. So weight 1 would be multiplied by input 1, weight 2 would be multiplied by input 2, and the bias would be multiplied by 1, which is just really the bias. So, and then you add those values up, and that's the sum of the output. And then I'll show you guys later. It's a little hard to explain with words, but when we get that sum value, that's not what we're going to output. We also want to squish the value into the range of 0 to 1. And it's just kind of mimicking how a neuron either fires or it doesn't, or it's fires a little bit. I don't know if real neurons actually fire just a little bit, but that's kind of what we're going with this neuron here. So it's going to, in the end, we're hoping it will output a value ranging from 0 to 1. And then we'll decide on the action based on how big the value is in the output. So in this example, I'll probably be using, it does one action if the output is 0.5 or less, and a different action if it's 0.5 or more. So that's how the neural network will start deciding things. And the math behind it learning is something I'll be showing you guys in Roblox Studio. It's more simpler than you'd think, but really it's just changing these weights so that when you give it a certain input, you get the expected output more often, or at least closer to the expected output each time you train it. So that's it for the visual explanation. Now let's go into Roblox Studio and actually start coding this into existence. All right, so I have loaded into a base plate template. So there's nothing here. The first thing we're going to do is add a module script to replicated storage. This is going to house our Perceptron. We're going to name it as such. So I'm going to rename it to Perceptron. Perceptron. And I'm also going to rename the variable that's inside the module script. That's called module, and I'm going to rename it to the name of the script. And the code today will just all be in a module script, and we're not going to implement object-oriented style programming. So we're not going to do any classes or objects. We're just going to have it located within a module script. And you're only going to have one, so you can't create multiple perceptrons from this module script. It's just going to be one, and if you want more, you're going to have to copy and paste the module script. To start this out, we are going to want to add some variables, and we're going to include it. We're not going to do a local variable like this. We're actually going to include the variable inside the Perceptron variable. That's a table right now, so we're going to add some properties to it. The first one we're going to do is add weight 1, and we're just going to set it to 0 right now. We're going to change this later, but as you saw with the graph I showed before with what represents the Perceptron, we have weight 1 and we have weight 2. And we're going to set these to different values, but for right now we're setting them to 1 or to 0. And then what we also see in that graph is that we want a bias. So we're going to include a bias here, and it's going to be set to 0. That one's going to stay as 0 for right now. And another thing we're going to include is the learning rate. And we're going to set that to 1 right now. Now what we're going to do is we're going to create, well, actually I should have done it above these variables, is we're going to create a local variable this time. And I'm just going to call it random. We're going to create a random object that will be our random number generator. The reason we're creating a random object is because if we test our neural network, we want to be able to use the same random numbers each time to reproduce what we test. We don't want it to be a new set of random numbers we generate each time we test unless we switch the seed. So usually we keep the seed the same, and I'm just going to keep it to 1 for right now. And now we're going to change these zeros I had for these weights to actually, it's going to be randomly generated, because we don't want the weights to equal 0 on initialization, because later we'll find that if it is 0, the neural network won't learn. So let's change this to, we want this to be a value from like -1 to 1. So if we take our random object and do next number, this here will generate a number from 0 to 1, basically. It'll be a decimal usually. And so if we want it to be from -1 to 1, what we're going to have to do is we're going to multiply this by 2. So now we have a number that ranges from 0 to 2. And then we're just going to subtract the total by 1. And this will move the 0 to the range 0 to 2 to the range of -1 to 1. So now with this, our weights will be a random number from -1 to 1. So let's continue on to our first function that we're going to want our Perceptron to have. And that is going to be, we're going to call the function feed. But we're going to keep the first variable, we're going to name it self, and basically I want to be able to access these variables through the self variable. So this is a little special thing I figured out lately, is if you do type of, and then you take the table you want to get the I guess the type of it. Type of perceptron. Now if we were to access the self variable, you can see that it has the bias weight 1, weight 2 learning rate that perceptron has. Basically, we're telling it that the first variable will be the same type that we have created here. This is the name of the variable, and this is the type of variable that we're working with. This isn't, you don't need this. It's just that if you only have self, now when I try to access any variables, it doesn't give me that quick menu, which is not what I want. I want that quick menu. So let's add that back. We're also going to want to add the input. We're going to expect 2 inputs, but it's going to be in one variable. So it's going to be like, it's just going to be an array. Index 1 and index 2 are going to be the inputs. So we have our function created called feed, and we're taking the input, and we have the self variable here. The first thing we're going to want to do is we're going to want to calculate what the sum of the output neuron should equal to. And in that case, we are going to be taking our input 1. Well, let me get these into variables first. So input 1 is equal to input index 1. Local input 2 is equal to input index 2. So I'm making an assumption right now that the inputs we're getting has 2 elements in the array, and it's the input 1 and input 2. And now that we have the input variables, we can start to calculate what the output should be. So we're going to create a variable called sum, and it's going to be equal to the input 1 times self.weight1. So basically we're taking the input, multiplying it by the weight that is associated with that input. These are associated with each other. Then we're going to put these into parentheses, and we're going to add and create another parentheses. We're going to take input 2 and multiply that by self.weight2. So now we've looked back at the inputs and the weights connected and added those values together. And at the end, we're going to add the bias. And that is going to be equal to our sum, our total sum. Now, that's not what we're going to be outputting. That's not going to be the final value of the output. We just summed everything before it. We want the output to be from the range of 0 to 1. 0 meaning it didn't fire, 1 meaning it completely fired. It's a neuron. We're kind of thinking of it like it's a brain neuron that fires and doesn't fire. So we don't want this sum to be beyond the scope of 0 to 1. In this case, we're going to be using the sigmoid function. And if you give the sigmoid function a number, it will output a number from 0 to 1. Even like a really big negative number, the bigger the negative number, the closer it is to 0. The bigger the positive number is, the closer it is to 1, but it never reaches them, but it gets closer, the bigger or smaller the number. We're actually going to create this function at the very top because it's not going to be part of the module. We're just going to call it sigmoid, and it's going to take a variable called x, or a parameter named x, and it's going to be a number. And the sigmoid function is just, we can just return it on one line. We take 1 divided by, and now we're going to add parentheses, so we get this total value. It's going to be inside the parentheses 1 plus math exp, which is e to the x, basically. Don't worry if you don't understand what this means. This is the unimportant part, really. It's just stupid math. So we're going to put negative x into math.exp, and that should return the sigmoid value. So what do we do with this function? Well, we're just going to now in our feed function return sigmoid, the function we just created, and we're going to include the sum in there. So now what it's returning is a value from 0 to 1. So that is the feed function. We're also going to include some other things in the return statement just in case we want some more information about it. I'm actually going to also return the sum. So it's going to be return a tuple. It's going to return 2 variables. Sure, it returns a value, but this doesn't learn yet. If it's wrong, it doesn't know how to correct itself. It doesn't know what it needs to do. So we're going to do a new function, and it's going to be called train. It's going to take the same self parameter from above, and then it's going to take the same input parameter as above, but it's going to include a new one called expected. So this expected variable is going to be the output we are expecting, and this usually ranges from 0. It's either 0 or 1. So what the training really does is it's going to change the value of the weights and the bias so that next time you give it the same input, the output will be closer to what you expected it to be. And to do this, we have to do some math. Luckily, for a one-layer neural network like a perceptron is, it's pretty simple. We are going to call the feed function from before. That's not what I wanted. Oh, whoops. You don't want the local there. Self feed. And we're going to give it the input that we have here. And we're going to, we do want the local because we're going to want to capture the output of this function call. We're going to get output as a variable and sum as a variable. Now that we have the output in sum, got to calculate how well the perceptron performed, because this output wants to be, we're hoping that the output here is going to be equal to the expected, or at least really close. So we got to let it know how it did. And to do that, we got to create a cost function. The cost is just going to be, output minus expected. And we're actually going to square this. So math.square, or power. We're going to square it, but we're going to use the power function. So we're going to square it. So put 2 in the power variable. So that is our cost function. Basically, this tells us how well it performed. The bigger the cost, the worse it did. So we want this value to be equal to 0. Because if output and expected are the same number, the value here will be equal to 0, and 0 squared is still 0. But the worse it performs, the wider the gap of output and expected, the bigger this cost variable is going to be equal to. Meaning, it did a terrible job and really needs to correct itself. Calculate what our error is, which is basically the derivative of the cost function. So, derivative is a fancy word. You'll learn that later in math class if you haven't already. Probably your senior year of high school. But it's pretty simple derivative here. We're just going to take the output minus expected, and then we're just going to multiply this value by 2. That is the simple derivative of this cost function we defined up here. So now we have the error. What do we do with the error now? Well, we can start changing the weights now. So we're going to change weight 1. So we're reducing the weight 1 by the error multiplied by the input we got. So the input we got for this one is input 1. And we're going to multiply that by the learning rate. And that's all we got to do for weight 1. Weight 1 has been changed to what it needs to do to be better. But we got to do the same thing for weight 2 now. So I just copied and pasted that line. And I'm going to change this to weight 2 and change this to input 2. And now we've got what weight 2 needs to do to correct itself. Now, the last thing we need to do is change the bias. So the bias starts at 0, but it will change over time. And basically, the bias is just changed by the error multiplied by the learning rate. So it's very simple. That's all it does. And that's it. It learns. Like, it's so simple. You wouldn't expect such a little amount of lines to actually be doing something. But it does learn. It learns very simple things, of course, like I've explained, but it does indeed learn. So I'm going to go into server script service now, and we're going to add a script. And we're going to require the perceptron. Whoops. First, let's make the variable name. That's in server script or server storage, and it's called Perceptron. Oh, I put it in replicated storage. I'm not sure why I did that, but you know, that's fine. Okay. Usually I would put it in server storage unless the client also needed a Perceptron for some reason. So here we go. We required it. So now let's make some training, I guess. Let's create a function called train. And it's just going to be Perceptron train. These are just pure examples and they mean nothing, but these are what we're going to use to test how it trains. So let's say we give it the input 1 and 0, and we want the output to be 0. And we also want, if we input 0, 1, we want the output to be 1. Well, this is our training function. Let's see how it does first by printing out or local output equals Perceptron feed 1, 0. And then we can print output. Then we can do another one, output 2. Perceptron feed 0, 1. So before we call this train, let's just see how it calculates and make sure we don't have any errors here. Let's run the game like this. This won't run yet, but we'll test it later. We do have an error while loading. Okay. Missing argument number 1. Oh, I see. It needs... Oh, that's... I forgot. Okay, I don't know why it pops up. Okay. So what I did, I made a mistake. I did a period instead of a colon. Use these to call next number. Otherwise, it won't work. Yeah, I made that mistake. Let's try that again. Okay. So it outputs the value here. So our first, it returns 0.71. What are we expecting it to be? Well, we're wanting that to be 0. So that's far off. That's pretty far off. And then we want the next one to be 1, and that's 0.29. So that's bad as well, about equally as bad as it could be. So now let's test this training function here. And we're going to copy this as well down here. So we print out the outputs after it trains again. Print after training. Okay. We're going to call the train function. Let's see how that works. Let's see if that works. Well, look at that. After training, look how much closer this 0.7 is to 0. It went to 0.4. This 0.2 went to 0.79. So it's getting closer to the values we told it should be within these two lines. Now, if we would train this multiple times in a row, let's put this in a for loop for I equals 1. Whoops, for I equals 1, 10, so we're looping 10 times. Do, and we're, what happened here? Okay, let me make the screen bigger. Here we go. So 10 times we're going to call the train function. So now this is being called 10 times. Let's see how much better it does training 10 times rather than just once. And now it's super close to the values we were wanting. So it's pretty cool. It's like, oh yeah, it's learning, but it's just printing out these numbers that mean nothing. How are we supposed to use this? Well, here's the cool part. So imagine we're playing Pong, and you give it the inputs of where your player is, or the AI player is, location on the y-axis, so up and down, and where the ball is on the y-axis as well. So we could have it learn that if it is below the ball, it needs to go up, and if it's above the ball, it needs to go down. That's Perceptrons, like I've said, are limited in what they can do, but they can play Pong, and they can play Pong really well. Now, they're just following the ball, which is very simple, and we could code that way easier than using a Perceptron, and it would be better. However, this is cooler, and it teaches you the very basics of machine learning. Now, I'll show you guys an example of it actually being used to play Pong. I'm not going to show you guys how to create the game Pong. Unless you want to in a future video, I will. However, I'm just going to cut to when I finish creating Pong, and I will be using this same exact module to code Pong. So, I'll be right back with that. I need to go create Pong now. All right, I made the board for Pong, but it's not coded at all, but this is just going to be kind of the base that we're working with here. We got the ball. Player 1 probably on that side, the AI will be on the right side. And that's just how the Pong is going to work in this test case here, but now on to the actual coding the game part. All right, a little update. Now when you play it, the camera gets set to the Pong board, I'll call it, and you can move your player now. So it doesn't go above or below the board, it stays in bounds, and yep, so next thing I need to do is code the ball to bounce and go all around, and then the final part will be adding the AI to the other player. Okay, so I've got the ball bouncing. It bounces off the walls and the players, and if you actually win or lose, I guess, it resets the environment of the Pong game. So if I lose, so the last thing I need to do is code the AI to actually start using the neural network to decide which way it will go, up or down. And it will determine that given the inputs of where the ball is up and down, like location-wise, as well as its own location of its player, which is this paddle over here. Okay, guys, this is actually kind of crazy. It's actually insane. It already plays Pong. I didn't need to train it. I guess this happens sometimes where the weights are just automatically set to what they need to be in order to work in this sense. I was not expecting this. So I'm going to try to find like a seed for the random weight application so it like fails to play Pong and it actually show how the training works. But so far I think it's unbeatable when the ball is going at this speed because it's slow enough that you can catch up to the ball no matter what. And it just really, it follows it. So I just lost there.
Okay, so this is what I was more expecting the AI to do right off the bat. As you can see, no matter where the ball is, it just goes up. That's how I was expecting it to be, with it just being perfect right out of the gun. That was surprising, to say the least. But yes, this is what we're looking for. The one time I'm looking for it to be imperfect, of course, it was perfect. Usually it's the opposite. All right, so let's get the training going in. So I just had a little thing where it records each frame. How do I even explain this? It's a little bit hard to look at, but I made this Pong game as quick as possible. So basically, it records all the frames of the game, and then after the game finishes, it will go back, loop through the frames, and the frames just has information for where the ball was, where the AI was, and then where it should have gone. That doesn't mean it went there, but where it should have. All I gave it was that if ball X is above AI, or if the ball is above the paddle, then the paddle should go up. The opposite, then the opposite, So I commented out this, so now it should train after the game is done. I also need to make sure that the frames disappear or reset after the game is over. So now let's see how it trains. Okay, so it's starting to go different directions each time the game ends. That can be... Oh, look at that. Now it's starting to play perfectly. Why it went too far sometimes, like it corrects itself too much, that just might mean the learning rate's a little too high, but it just luckily eventually hit perfect where it is, hitting the ball right where it should be, right in the middle. So yeah, it didn't take long to train at all. This would be considered probably a perfect trained AI right here. You would save the weights. You could add a function to the Perceptron MrModuleScript and call it save, and then it would just copy the weights and the bias of the neural network, and then you could later load it. That's not something I'll show in this tutorial, but that's just if you ever want to make a neural network and want to save what the values it's learned, you gotta save it somehow, and you gotta add that functionality yourself. But yeah, so that's the end of this tutorial. So this is just hidden the very tip of the iceberg when it comes to AI and machine learning. And of course, this isn't really a practical use case. I'll look, it learned wrong again, but now it learned again to recorrect itself. Anyway, that you would probably want to lower the learning rate on this for it to learn a little bit better. But as I was saying, this is the tip of the iceberg. This isn't the most efficient way to do this. I mean, it's so much simpler just to code the AI to just go up if it's below the ball and down if it's above, rather than using a neural network and training it to mimic that behavior. But this is just ABCs of learning how to use neural or perceptrons, I guess. And we will be going into more advanced cases like tic-tac-toe, where tic-tac-toe cannot be learned perfectly by a perceptron. There's just not enough neurons, not enough layers, and not enough weights. So in future tutorial, I'll be showing you guys how to make a multi-layered perceptron. Some would just call it a deep neural network, and it wouldn't be too deep, but it would be way bigger than the very small neural network we have working here. That will be able to play tic-tac-toe and do a lot of more advanced stuff. So yeah, I'll be showing you guys how to do that in a later tutorial. I hope you guys liked this video. If you did like it, please consider subscribing, as I am a smaller channel trying to grow. And I'll see you guys in the next tutorial. See you guys later.